Hello. I'm recording 6.3 and 6.4 back to back. Nice to see your face again. First name, last name, class period, all that jazz is popping up on screen, and you're being prompted to ask those questions or answer those questions. Let's go ahead and jump into it. So, the 6.4 notes. What did we just look at in the 6.3 notes? We looked at the 45-45-90 triangle. Well, now we're looking at 30-60-90 triangles. Notice it's still a right triangle because of the 90-degree angle, okay? So let's kind of dive in to what we're going to see here. Consider an equilateral triangle with side lengths of 2. So this has a length of 2, this has a length of 2, and this has a length of 2. Use your compass, no, to construct the perpendicular bisector. So here comes the bisector of AC. So here's the middle. We're going to go right through the middle of it, like so, okay? I really wanted to stop at the dot. There we go. Whatever. I almost touched the dot. You get the point. And now we have a right angle. Whoops. Now we have a right angle. And if it's a perpendicular bisector, that means that we have now just created little pieces that are each 1 and 1 long. Okay? So when it asks here, and it says to label the point of intersection D, which I'll do that. So how long is AD? 1. How long is BD? We'll figure that out in a second. If this is a equilateral triangle, because it's 2, 2, 2, in an equilateral triangle, all three angles are 60. So this right here is 60 degrees. So B to A to C is 60 degrees. And A to B to D, well, if this is a bisector, that means we just split the 60 in half, and now it's 30. And then, of course, ADB is a right angle because it's perpendicular, so that's 90. There's our 30, 60, 90 triangle. Nice to meet you. So the one thing that we're still looking for is BD. It's a right triangle. We can use the Pythagorean theorem, and we're solving for a leg. So it's the square root of hypotenuse squared minus leg squared, which is the square root of 3. 4 minus 1 is 3. So let me go ahead and write that there, root 3. So there's our lovely 30, 60, 90 triangle. And just like the 45, 45, 90 triangles, we can blow that up. We can shrink it down. We can have a triangle with any kind of size, but it's always going to follow the same pattern. And what pattern is that? Well, let's say that the short leg is K long. Well, comparing it to the original, what's the relationship between 1 and 2? Well, the hypotenuse is twice as big as the leg. So the hypotenuse here we're going to call 2K because it's twice the size of the leg. And then comparing the short leg to the long leg, well, we simply multiplied by root 3. Right? 1 times root 3 equals root 3. So we're going to call this K root 3. A little more going on in this one, I will admit, which is why it's coming second, right? The legs are no longer the same like they were in the 45, 45, 90, okay? So each side is different. So the short leg gets multiplied by root 3 to get the long leg, and the short leg gets multiplied by 2 to get the hypotenuse. Or you can look at this the other way around, right? We can take the hypotenuse and divide by 2 in order to get the short leg. We can take the long leg and divide by root 3 in order to get the short leg. So you got to think of these paths, right? So take note of what you're given. Oh, I'm given the hypotenuse. I can then solve for the short leg by dividing by 2. The answer, 8. Right? That's the relationship between these two. Every 30, 60, 90 follows the same pattern. And then we multiply by root 3. We multiply by root 3 in order to get the long leg. So that's 8 root 3. What are we given here? This hypotenuse is 22 root 3. Interesting. That has the root 3. Remember in the previous notes how, it doesn't have to look the same. It just has to follow the mathematical pattern. So even though it's not a whole number, that doesn't mean it breaks the system, okay? It doesn't mean it breaks the system. It's just doesn't look the same, but it's still going to follow the same mathematical pattern. Okay, how do we get from the hypotenuse to the leg, to the short leg? What do? We divide by 2. Don't overthink it, just like we did right here. And 22 root 3 divided by 2, 22 divided by 2 is 11. So 11 root 3 equals x. That's the short leg. And then how do we go from the short leg to the long leg? You multiply by root 3, just like we did over here. And when you do 11 root 3 times root 3, well, voila, root 3 times root 3 just becomes 3. So 11 times 3 is 33, and that is your y value. So does it look the same? No. But I'll say it once more, it follows the same mathematical order, okay? So how about you do this one? Here's a question. Highlighting that so I remember. If this is the short leg, tell me, what is the length of the hypotenuse? And answer. What did you do? You should have simply multiplied by 2, and you got 20. If this is the short leg, what is the long leg? You multiply by root 3, so x becomes 10 root 3. That one looks nearly identical to the pattern that we're used to, right? It's got a root 3, this is twice as big, right? It's easier to read the math here, right? But there's no denying that 11 root 3 is half of 22 root 3. Even though it's not a whole number, it's still twice as big, just like 20 is twice as big, okay? Okay, here's one where it's a little weirder. Let's have you do this one as well, highlighting. If this is the short leg, what do we do to get the long leg? And answer. That's right. You multiply by root 3. And this time when you do the root 3's, it just becomes 3. So 2 times 3 is 6. Why does it just become 3? I mean, plug it into your calculator if you don't believe me. Root 3 times root 3 becomes 3. And you get 6. I'll do this one. We're going to double, and we get 4 root 3. 2 times 2, 4. Let's have you do one more. Here's the long leg, and we're trying to solve for the short leg. So we're going the opposite direction. Here we took the short leg and solved for the long leg. Now we've got the long leg and we're solving for the short leg. So what is the length of y? Well, if we're going the opposite direction, we're not multiplying by root 3, we're dividing by root 3. So that just cancels it out, of course, right? Bye-bye, and you end up with 25. And then you double it and you get 50. Same thing over and over and over. And in the classwork, I mean, there's not going to be much variety. It's not, I mean, these lessons are very straight to the point, short, sweet, and to the point, right? Not going to be much variety on the classwork either. So you ought to be a super genius when it comes to these. So The length here is, this is a long leg, it's 24, and we need to solve for the short leg. So we divide by root 3, and this is one of those situations where, oh shoot, right? We need to get rid of the radical in the denominator. And remember, it's as simple as multiplying it by itself. Because when you do a radical times a radical, it cancels it out. So we end up with 24 root 3 over 3. But don't ignore the fact that 24 divided by 3 is 8. So we can actually reduce that down to a nice, pretty 8 root 3. And then how do we go from the short leg to the hypotenuse? You simply double it. (16 root 3). Okay. So, recall. Okay, we recall. We were just doing it, right? There it is. Blah, blah, blah. Okay, so let's do the same. I mean, this lesson ought to feel a lot like the previous one, right? It's just that, oh, we're doing this for 30, 60, 90 now. So here's our short leg. What do we do with it? We double it to get the hypotenuse, and we multiply it by root 3 to get the long leg. That's what we just did 6 times over. And now we find sine of b. Sine of b, that's opposite adjacent hypotenuse. Remember SOHCAHTOA from the previous video, I mentioned that. So sine is opposite 3 over hypotenuse 6, which reduces down to a half. So sine of b, or sine of 30, right? Sine of 30 degrees, that's what b is a half. And cosine adjacent over hypotenuse, so 3 root 3 divided by 6. 6 reduces to a half, but we still have the root 3, so root 3 over 2. And then tangent, opposite over adjacent, 3 over 3 root 3. This ought to feel familiar, how, oh, those are canceling. And then I need to multiply. We were doing something eerily similar in the previous notes video. So it reduces, cancel out the radical, and you end up with root 3 over 3. So if we look at this the other way around, we're looking at angle C now. And let's get rid of these distractors, O, A's, and H's. And let's just do them in pink now. This is opposite, this is adjacent, and this is hypotenuse. Remember, in the 45, 45, 90 triangle, I'll even show you, it didn't make a difference because O and A were the same, right? The legs were the same. But now when we switch roles, we've actually got different numbers. So this is going to be different, okay? So opposite of C is 3 root 3 over hypotenuse, which is 6. And we get root 3 over 2. So those are different, right? The sine values aren't the same here. Cosine of C is adjacent, 3 over hypotenuse, 6, and we end up with a half. And then tangent is opposite over adjacent, which is 3 root 3 over 3, which cancels out to become root 3 over 1. Now, do you remember something from lesson 2? When we did our notes in lesson 2, I took notice of the fact that, wait a minute, tangent of the other angle in a triangle is always the reciprocal. Right? You remember that? Tangent is always the reciprocal, and then sine and cosine could be switched places, right? What was sine of one angle becomes cosine of the other. What was sine of that angle becomes cosine of the other. Well, guess frickin' what? We're still looking at it. Just because they're super special numbers, 30, 60, 90, doesn't mean that's not going to happen, right? Look, what was sine became cosine. What was cosine became sine, right? And then is this the reciprocal? You might look at this and go, well, that's not flipped. Look back a step. 1 over root 3 flipped becomes root 3 over 1. So yes, they are reciprocals. All right, let's do it again. We are given the hypotenuse, take half of it to find the short leg, and then slap a root 3 to get that long leg. And let's see what happens. There's B, opposite adjacent hypotenuse. We end up with 4 over 8, which is a half. Opposite over hypotenuse. Adjacent, 4 root 3 over hypotenuse, which becomes root 3 over 2. And tangent of B, opposite over adjacent, 4 over 4 root 3, which reduces to 1 over root 3, which we already know up here we already did that. So root 3 over 3. So despite the triangle changing size, sine and cosine remained the same, right? We're learning the same thing over again as the previous lesson. It doesn't matter how small your triangle is or how big your triangle is. Sine of 30 is a number that is always a half, right? That's not changing. That's what we're trying to really reinforce here. No matter the size of the triangle, sine of 30 is always a half because of the reducing, right? So, real quick, tell me, boom, what's the answer to this right here? You should have thought to yourself, and what's the answer to this right here? Then I'll do the question. So what's the answer to both of these? Using what we just said up here, you should, boom, immediately say, oh, I just need to switch these values, right? This is root 3 over 2, and this is a half. And then I take the reciprocal over here, right? Or you could just look up here and realize, oh, it's the same thing on repeat, right? Yes, it is. So I'd imagine you got that right. Do we need to do it again? No, let's not. Let's not be that boring. Same thing, same thing, same thing. Sine of 30, no matter how big or how small your triangle is, no matter what the length of the legs are, it's always going to be a half. And cosine of 30, no matter how big the triangle is, no matter what the lengths of the legs are, is always going to be root 3 over 2. And tangent's always going to be root 3 over 1. And then the other way, when you do, instead of sine of 30 and cosine of 30, we're doing sine of 60, the other angle inside of the triangle. Sine of 60 is always root 3 over 2, and cosine of 60 is always a half. And I accidentally wrote the wrong thing. That's 60, my apologies. 30 is root 3 over 3. Always, always, always. No matter how big the triangle, no matter how small the triangle, no matter what the legs are, no matter which, it doesn't matter what triangle we look up here. If you were to take sine of 60, it is what it is. You punch it into a calculator, boom. Okay, so we had a decent handful of questions in there. I think we're good. This video was just a teensy bit longer than lesson 2. Or lesson 3, but that's okay. So thank you for watching, and that's that.